Okay, so please go ahead.
So I'm interested in the limits of sophomore and kind of library generation of sufficient size and whether there are classes of chemicals to for which it works well and other classes which it doesn't, and kind of those issues.
So when we say library, I know we have some members from the pharmaceutical industry here. So when we say a library, we mean tens of polymers, actually, so not 40,000. That's large for us. We have to make each one. We're almost at the point where we actually don't need to do a library screening. We can predict the structure. So your second question related to the scope, or what kinds of molecules can be detected. I don't want to oversell the technique, but we have yet to find a class of molecules that the technique doesn't work on. I did not show data today. We're in the process of submitting some work where we've been able to recognize carbohydrates. You can actually make chiral Kaufman sites. You can see, if any of you work on carbohydrate detection, they've got to be the most difficult molecules in your body to try to distinguish. Basically, sugars look almost identical, but Kaufman can actually recognize. So at this point, I think we have access to all the ways that natural systems have evolved to make recognition sites, right up until even chiral molecules, but proteins, and so hopefully that answers your question.
I have another question for you, Michael. How independent is the technique from the type of nanotubes you buy or use, and the thickness or density of the mat and things like that?
So it's so those kind of variants don't show up in our data, but oftentimes in our, so for much of the data that I showed you, we had ensembles of carbon nanotubes in solution. It's true that if you try to make nanowire transistors or nanotube transistors at the single device level, you do get device-to-device variance. But if you look at an ensemble, we don't see that variation. I did show where we have sensors optically. Basically, if you address each nanotube optically, you still get an ensemble of data, but it's also at the single molecule. It's at the single nanoparticle level. So again, there's enough statistics that you can get the recognition, very independent of the source of nanotubes. That was your question, right? If you have different sources. So hopefully that's clear.
I wanted to ask a question, I think, of Anu and Tim. I didn't hear any mention of phase. Sort of chemistry, but sort of gas versus liquid. What are the issues? Are there issues there that we should be sort of raising?
Well, maybe I'll start. Gas phase is easy. You don't have to desolvate the molecules. So I'd say gas phase sensors are maybe an easier target. We've done a number of liquid phase. You have to really make sure you anchor things down, because any movement of a nanotube will be a large background signal that will overwhelm other things. And there's also, things get complicated with the nanotube. With p-dope, you get an electrical double layer on it. So there are many some other complications. I think there's actually some opportunities in how to yield some of those complications to make things. But you can do both, and we've done both.
So it's just the opposite problem. We should probably talk. We can do liquid sensing a lot easier than gas molecules, particularly because we're dealing with an evanescent mode that comes out of our waveguide, and that evanescent mode has to interact with our target analyte. So if you have a liquid, there's liquid all over, the concentration is large around the waveguide. But if you have a gas molecule, then of course you have only a certain limited number of molecules interacting with that evanescent wave. So it's the opposite problem. We can do liquid sensing a lot easier than we can do gas sensing, but there are ways in which we can overcome it simply by making those pedestal waveguides that I showed you so that there's more of the mode sticking out and therefore more interaction with the analyte.
Hi, this is for Bill. Thank you for the videos. Love it. Are you able to distinguish between two sources of motion?
Are we able to?
So if I have a big movement and a little movement on top of it,
Ah.
and I'm looking, can I?
So that's the direction we've done some work. It makes it harder. So if there's a small motion on top of a big motion, typically we have to first remove the big motion and then amplify the small motion. It's much harder for us to. We don't have a clean way like this one to amplify in the course of an already large motion, although we're interested in that. One way that we kind of focus, if you will, on one motion over another is to do this temporal filtering, where we narrow band temporal filter and then amplify whatever we see at that frequency, and that often separates out different motions for us. For example, with the normal modes, that's what we did.
Thank you very much for a number of very interesting talks. Bill, I have a kind of an annoyingly obvious question, which is, have you ever done or considered doing this amplification on a single carbon nanotube that's sort of standing up, and see if you can see the modes going through it, potentially in response to certain stimuli?
No, I'd love to.
I think that'd be potentially interesting. And then the second question is, I know that so you sort of showed almost the reverse double pendulum problem, but the actual double pendulum or multi-end pendulum problem, I know there's some people at MIT who are working on that, but would there be any, it's notoriously, I guess, impossible or difficult to model. Would this type of technology enable more insight into sort of the originations, if you will, or the underlying reasons that you might sort of experience a certain direction of the double pendulum?
I don't know enough about the problem or about where the frontier of the research is on that to be able to say.
Okay, thanks.
There's a question over here in the front.
So, Bill, your images are 2D fundamentally, your videos. So you get 2D directional information. Have you attempted, or do you think there's a way to get three-dimensional vector information?
Yeah, so you could really just go out to 3D using pretty much the same technique we did, but extending everything to 3 dimensions. So you'd need a 3-dimensional decomposition of volumetric data, and we have those. And you could, instead, you'd write the whole volume as a linear combination, as a sum of these little now 3D wavelets, each of them oriented at every position, orientation, and size. And you could do the same thing. We haven't done it, but there's certainly, with medical data, you could have the data set to do it, or geophysical data.
What are some of the interesting data that we should be getting in nano with volume imaging at the small scale? Take another question. I saw there was a hand at the back. Oh, there's a hand there, and then gentleman.
Excellent talks, Professor Freeman. Do you envisage this being quantitative for things such as progression of diseases, Parkinson's disease or Alzheimer's, in terms of the motion aspects?
Right. So we have done had a collaboration with doctors at Brigham and Women's studying neuromuscular diseases, and it's interesting. My experience with this collaboration was that they started out looking at the videos and were very excited about it, and then it just quickly became just simply a measurement problem, not a visualization problem, of just measuring the motion as a function of time of the patients and applying mathematical transformations on that to somehow quantify the degree of instability or the type of it. And then we didn't use these techniques after the initial meetings, really. So it's these techniques are more kind of exploratory, the way you might use a microscope to visualize a phenomenon, but oftentimes to actually measure the underlying things, you may not need this visualization.
Okay, thank you.
Just what are the other panelists, to put on Bill's point that he'd love to identify some ways to collaborate? What do you see as the interesting ways that could be intersections between the things you like to measure and Bill's work?
Well, I mean, I think that sensing computational is bringing out wavelet technology or wavelet methods like you're using, and even in electrical or you're doing there's so much engineering information you mine that can really help a two-dimensional sensor space, that those mathematics would really apply. And I think we got a lot of resources in MIT to help with that.
Just let me comment. I have a collaborator at UCLA, and he's and we're having a debate on the definition of what a sensor is. There's a whole separate set of there's a whole separate community that calls a sensor really diverse data and algorithms brought together to inform some state. And he's proposed that, particularly in the human body, that every sensor partially encodes for every state. It's a very intriguing possibility. Maybe it's a self-serving assumption on his part, because it means maybe algorithmically we could take your Fitbit and we can determine if you have heart disease or if you're going to develop cancer. So in theory, as far as I know, that has never mathematically been proven, this coupling of all the states. Physically, it's possibly true, but it's led to an interesting debate. Do we need very selective sensors? Do we need sensors so selective that we really reproduce laboratory equipment and we put it into a cell or put it into the body? Right at the time where data scientists are extracting enormous amounts of information from data we've had in front of us all along. That's how I see the context of your work. It's really the algorithms is extracting information that it's hard to see. So I don't have the answer to that.
So I think that it's a really interesting thought. When I listened to all of you talk, carbon nanotubes would be great to use. The selectivity that you bring with your molecular recognition, cough more, nice name, would be useful. And also trying to select, I was thinking about the oil and gas pipeline detection. If there's motion and it's about to have a leak, you can actually detect it. So in my mind, I think multimodal detection is what's really very, very valuable. So you don't just use one kind of sensor to guide you, but you have multiple ways to inform you about what's going on.
I'm going to leave you with wanting to ask more questions to get back a little bit on time. So I'll leave it with, I think that's one of the exciting opportunities about bringing these communities together, to look at those interesting intersections, but different approaches of sensing and bringing different expertise from optics to photonics to computer science together. So I want to thank, again, the panelists.